My name is Eleanor. I am a BAMS student in Remote Sensing and Geospatial Sciences out of the Department of Earth and Environment here, and my Keystone is titled The Arctic on Fire, Mapping Change in High-Latitude North America. So I choose to focus on the Arctic and subarctic because of the region's unique vulnerability to the effects of global climate change. The most kind of direct way to explain this is that every bad effect you've heard of happening due to climate change, think things like temperature increase, more insect and disease disturbance, more frequent and intense wildfires, are exacerbated in high latitude regions like the Arctic and subarctic when compared to lower or mid latitudes. So for these reasons, it's really important that we have a holistic and accurate understanding of the landscape properties of these regions, as well as kind of the challenges facing them, because this information is vital and foundational to any further research or any actions taken in the area. Like I mentioned, I study something called remote sensing, and at the Center for Remote Sensing here at BU, we focus on passive satellite-based remote sensing. So the way that that works is as electromagnetic radiation from the sun comes from space, it interacts with different materials on Earth's surface in different ways. And Earth-observing satellites are able to kind of collect this data at a bunch of different spatial and temporal scales, and we can use it to understand a lot about kind of the landscape properties, ecosystem health, and all sorts of other things about the Earth. Satellite-based remote sensing like this is specifically important in Arctic and boreal regions because of the harsh conditions, the size, and the remoteness of the region that make it more difficult for researchers to put boots on the ground or leave instruments kind of in the area for longer amounts of time. So satellites give us a really consistent, reliable monitoring method to be able to keep an eye on the Arctic from other regions. My project focuses on using satellite-based remote sensing and machine learning to map annual land cover and disturbance regimes of high-latitude North America. I've worked on a larger initiative similar to this through the Center for Remote Sensing for a few years now called NASA Measures GLANCE, and all those acronyms are defined on the board if you're curious. But through GLANCE, we're creating global annual land cover maps for the 21st century at 30-meter spatial resolution. And both GLANCE and my Keystone project use this 7-class land cover schema. We map water, snow and ice, developed areas, barren or sparsely vegetated areas, trees, shrubs, and grass. And GLANCE as a whole is a really exciting new project that's coming out of the Center for Remote Sensing because it's the first time that anyone has produced a global record like this at the spatial and temporal scale that we're using. So it is a very kind of exciting initiative for the center as a whole. To do this, we use an algorithm called CCDC, or the Continuous Change Detection and Classification algorithm that was also developed here at BU. And how that works is it fits kind of that curved harmonic model to a time series of reflectance values across a whole lot of different bands and indices. After it kind of discovers these harmonic fits in the models, it identifies breaks, so where a previous model fit would no longer be appropriate to kind of the continuing time series, and then classifies the land cover based on these harmonic models. So you can see in this example on the screen, we're looking at time in years and shortwave infrared reflectance. The pixel is initially kind of a nice, healthy evergreen forest, that's the red model fit, and it's then clear-cut and recovers through stages of grassland and shrubland, and you can kind of see through time how CCDC is identifying these changes and classifying the land cover based on kind of what it's seeing in the reflectance in the spectra. My study region for this project is called the NASA Arctic Boreal Vulnerability Experiments Core Domain. You'll hear me call it the above core domain, and it covers most of Alaska and much of Western Canada, and the above domain was designed with kind of two main goals in mind. Number one, it covers a diverse array of landscape types. So you can see on the screen here, these are level 3 ecozones. The whole place isn't snow. The whole place isn't evergreen forest. It covers like a nice variety, and that's really important. And number two, the above domain was designed for scaling. So any kind of methodologies tested in this region and any discoveries that we have here can be reliably assumed to be accurate for kind of the rest of the global Arctic and subarctic. My research objectives for this project were primarily to assess how well GLANCE's global modeling methods are performing in the Arctic and subarctic, and whether it's doing a good job of identifying land cover and change, or whether nuances in this unique ecosystem kind of make it less accurate, less functional. And then with the assumption that the results were pretty accurate, I wanted to look at where and when we're seeing change, and then zoom in on a specific pervasive type of disturbance, which is forest loss. And forest loss in the high latitudes like this is really generally indicative of wildfires, which are widespread and very damaging. And forest loss was also the largest single type of land cover conversion we saw between 2001 and 2019. Starting off with the annual land cover maps, I found really great overall accuracy for kind of the entire time series between 2001 and 2019, as well as high annual accuracies for each product in that time range. You can see what the product looks like on the right there. Trees and herbaceous cover the majority of the area. And kind of what we can gather from this is that GLANCE is doing a really impressive job of informing us about what the landscape looks like each year in the region from outer space, without having to put anyone wandering around validating the data or anything like that. Moving into change detection, we also found a really high agreement for GLANCE's ability to identify land cover change and disturbance, with about 330,000 square kilometers of the region disturbed between 2001 and 2019. The distribution of that is in the map on the right. All of those colored pixels are areas that experienced a change at some point, and a lot of the more dynamic pixels, the yellows and reds, are in kind of south-central Alaska, along the Alaskan mountain range, which is an area that's very diverse and very spectrally complicated. When looking at the annual time series, you can see that there definitely is kind of interannual variability in how much change area we're seeing, but just by fitting kind of a linear trend to the data, we're averaging an increase of 800 square kilometers of change area per year. You can also see that the 2 years with the highest detected change area are 2018 and 2019, which are the two most recent years in the time series, both supporting this idea that change is becoming more commonplace. There's more conversion as we go through this 20-year time series. So from this, we can see that GLANCE is very successful at detecting the areas most affected by change, when the change is occurring, as well as how the region as a whole is being impacted by land cover conversion, which is really, really crucial data. And then finally, to look specifically at forest loss, this is the distribution of fire in orange and forest loss in red on the right. They're intentionally similar colors. I know it's a little bit hard to see the difference between the two. But this kind of spatial trajectory is exactly what we would expect from other fire products and things like that. You can see that there's less of this sort of damage in kind of the very high north of the region. That's because it's snow and ice, it's the tundra, there isn't forest to lose. As we look through the, again, annual time series, the top is the GLANCE detected forest loss, and the bottom is fire polygons. You can see a really similar pattern in these time series between the two sources. Both have that notable spike in 2004, 2005, and in 2015, which are both well-documented extreme fire years. And as we zoom in to the actual map on the right here, you can see that there is a similar pattern spatially as well. A lot of those orange fire polygons are covered by the red forest loss as well. Although they aren't exactly a one-to-one comparison, that's actually a benefit here because they offer us different information about kind of what's changing in this landscape. There we go. These data are obviously really interesting to scientists and researchers, but they're also very relevant to people like locals and land managers. That being said, though, data access can be very difficult if you don't know how to find data, download data, process data. So in the pursuit of making this easily accessible and usable to people of all sort of disciplines, I have put together a nice little app where you can explore all of the land cover data that I put together, all of the change data we were detecting, the forest loss, all of that very easily and accessibly. Alongside our GLANCE data, there are ancillary data layers, including protected areas like state and national parks, indigenous territory, as well as 3-level of ecoregion designations. The idea is that these ancillary layers allow you to kind of orient yourself to the landscape and get a better understanding of what you're looking at alongside the GLANCE data. In this example, you can compare indigenous territories and the forest loss data to see which indigenous nations are being most impacted by that. And then in this example, you can use land cover data to compare it to things like national parks and see what national park land cover classifications look like. Finally, my takeaways. Overall, we found that these global modeling methods perform impressively well in high-latitude North America and are able to accurately identify both land cover types as well as disturbance. We find from the results that land cover conversion from disturbance is becoming more and more widespread in the Arctic and subarctic, and that fire is a significant driver of forest loss, which is the largest single type of land cover conversion detected in the Arctic and subarctic. Overall, these annual land cover maps give us a better, more granular understanding of the state of the Arctic and subarctic and provide an accurate basis for any further research, land management, and more. If you're curious and you want to buzz around in the maps in your phone, you can use this QR code. Thank you. I'm happy to take any questions.
Hey, Ellen.
Hey.
So if you could fix one thing with Glance, what would you do?
For those who don't know, this is my advisor who runs Glance. I would add wetlands. I think a lot of the errors that I was seeing weren't the fault of the product as much as it's just kind of unique land cover classes that are only found in the Arctic and subarctic. So it'd be nice to kind of incorporate a way to be able to visualize things like that too. And they're important, yeah.
Nice job.
Thank you.
Great job. I have a question about the kind of timescales that you're talking about. So this is a, correct me if I'm wrong, relatively new ability to do the kind of satellite sensing at this level, and at this level of granularity in particular. And so much of what you're talking about hinges on this notion of change, right? And yes, an accelerated change over the time period that you have this data for, but I'm wondering whether there's anything that you can do to think about different cycles of change, thinking further back, and the ways in which, especially I'm thinking about the people who sort of speak back to the insistence on the rapidity of recent changes around, especially climate disturbance and fires, and think, you know, and say, oh, well, it's always been these sort of like different cycles of change if you really look over the long term. So how do you think about that in the longer term ideas around how, especially this sort of land changes in the kind of natural way? And what do you do with that? What do you do with that as a sort of rebuttal to what you're doing?
Yeah, are you thinking like longer term in the scale of like using
Historic.
Satellites or
no,
like long
I mean like
term?
long term. Like
yeah, I think it's interesting. I think you bring up some definite strengths of what we're doing here, as well as some obvious, you know, satellites have only been around so long, so how do we compare these new methods to traditional methods? I will say Glance is exciting because we're doing this annual change detection, which isn't something that other products do. It's pretty unique to have this spatial scale and this temporal scale for the whole kind of time series, as opposed to doing just a 2019 land cover map or anything like that. So right off the bat, I do think that there is potential to extend that further even in the satellite kind of era. So a lot of the data that we use goes back to like the 70s or 80s, depending on what you're looking for. So even potential to look at that time scale, I think, is definitely something that would be interesting moving forward. To speak to your point about times before that, I think that is very reliant on what data exists from other methods, right? I know a lot of, especially in the high north, a lot of people do have really robust fire history data because it's always been a concern, so you'll be able to find fire polygons and things like that historically, but there's definitely a complicated conversation around how you compare data from foundationally different methods, right? And how you kind of unify machine learning and things like this with these hand-drawn fire polygons from, you know, the early 20th, if not earlier century. Does that answer your question? Sorry, that was... I have a lot of thoughts on it. Okay, thank you guys. Yeah.